Okay, so then I want to move on to talking about numerics for the continuous problem, in particular numerical methods for a monge-ampere equation in the context of optimal transportation. So we talked about monge-ampere equation a few weeks back and how could we interpret it, and we looked at the fact that you can write down very simple settings where you don't get smooth solutions. You need some kind of weak interpretation of the equation. And one of the weak interpretations that we came up with was this notion of the viscosity solution, where we were basically doing, a second derivative test for maxima or minima, right? And using that to put smooth test functions below or above our viscosity solution and say how the second derivatives had to behave, or more generally how the value of our second order operators should behave on the test functions. So I want to talk about now, how do we build numerical methods that know that that's the definition of weak solution that they're supposed to try to capture. Okay, so this is the equation that we're trying to solve. Equals 0. I'll define this as an operator actually. And we'll just remind you what the definition of the weak viscosity solution was. So we said that U is a viscosity subsolution. If for every smooth feed convex, the way I've written it here, you saw in one of your homework columns that we could build convexity also into the PDE. Okay, so such that U minus phi has a maximum at x naught. Then we use this to say, well, now we know how the operator, the PDE operator, is going to behave when we plug phi in. And we know that it has to be non-positive. Okay, this was the setting here, so we had our U. U minus phi has a local maximum, so phi is up here. U minus phi is negative everywhere and 0 here. And we started with the observation. We started with the observations of the Laplacian, but said hopefully this works for other operators. And that if these guys are smooth, if U and phi they're C2, then essentially we're doing the second derivative test here, right? The second derivative of phi is bigger than the second derivative of U. We've got a negative sign in front of it, so it's really that this operator applied to phi should be less than or equal to this operator applied to U. Okay, now our challenge is, there's boundary conditions of course with that too, we'll come back to that later, but start here. Our challenge was to say, how do we build a numerical method that knows that this is what it's supposed to do? It comes to a point where second derivatives don't exist, but somehow it knows it has to do this instead. Finite difference methods turn out to be the easiest way to try to make this happen. your finite element, your Gaussian projection type methods are great when you have an integration of parts type definition of a weak solution. The viscosity solutions is very much an L infinity kind of theory where you've got maxima, you've got continuous things, and finite different methods are kind of natural for this setting. So let's try to write, for now, our method really abstractly like this. Okay, so I'm taking my, I discretize my domain, a discrete grid, and at every point I want to take my PDE and replace it with some equation that just depends on the value of u here and at various neighboring points. And then my PDE turns into this big system of algebraic equations that I have to solve. That's the game of finite differences. So somehow abstractly, we're trying to do something like this. Then instead of a PDE, we're going to have this discrete operator, H, looks like a grid spacing, for example. And this is going to depend on what point we're at, which is probably a grid point. It's going to depend on the value of u at this particular point. And it's going to depend on the value of u at other points, probably at neighboring points, I+1 or j+1 or whatever. So abstractly, I'm just going to say it depends on the value of u elsewhere. You would use this grid function, and we need its values at other various locations. And, of course, we're hoping that this somehow approximates our actual PDE operator. That if things are nice, this is approximately equal to our original operator at this point. Okay, now I'm going to try to play exactly this game here. What happens if phi and u are touching at one point and phi is sitting above u everywhere else? Right? Exactly the case where u minus phi has a maximum at some point x naught. And without loss of generality, it's fine to say that they touch at this maximum. So let's suppose that, or in this case, u minus phi has a maximum. So u of x naught equals phi of x naught. And u minus phi everywhere is less than or equal to the value at this point, so a maximum. Well, we'd like to have the same kind of property holding now, not for our PDE operator, but for our approximation to the PDE operator, that it's going to still kind of respect this second derivative type test. Instead of putting my second derivatives here, I put my approximation to my second derivatives here. So what we want, that fh of x, phi of x, and phi everywhere else is going to be less than or equal to 0. And if u is our true solution that we're trying to find, or maybe, the approximate solution in this case that we're trying to find, we're replacing this with fh, then we expect 0 to be equal to what we get when we plug u in here. Alright, so all I've done is taken this inequality that we said, this is what we expected to be true at the continuous level, and now I'm saying instead of doing this for my continuous operators, I'm going to try to require that my discrete operators also have this property. I could simplify this maybe a little bit if we assume that this is the case. Maybe I should use x naught if I assume that these two values are equal to each other, what do I have? I have x naught, u of x naught, phi is less than or equal to, same thing with u's. And this should be true whenever we're sitting in this situation where u is always less than phi. So whatever my function values at u are always less than my function values at phi.
So you're just replacing one entry with a phi?
I'm just replacing one entry. So what I'm assuming is that they're touching at this one point. Right? Everywhere else they're different, so I can't replace them everywhere else. But here, u and phi are equal to each other. Okay, so I have the same operator on both sides of this inequality, right? The same value of x naught getting plugged in, same value of u of x naught getting plugged in. Then different function values getting plugged into this third argument, but they're not just a random choice of different values. They're a choice of different values that satisfy this ordering. U is always less than phi. So what is this a statement of? This is a statement that says that I take this discrete operator, and actually, it's if I increase the value of my argument, I decrease the value of the operator. In other words, this is a non-increasing function in its last argument. This is exactly the equivalent way of saying it. fh is non-increasing in its last argument. This is the kind of scheme that we're going to try to build in order to solve an equation like this. And we'll do the proof. Then we'll be able to prove that if we can build schemes that do this under the right circumstances, we actually compute the correct weak solution that we're after. So I'm going to give us a definition. Schemes that do this are monotone. So a scheme fh of this form depends on x, it depends on u at that point, it depends on the function values at neighboring points, is monotone. If it is not increasing in the last argument. So any questions on the definition? I'm going to do some examples of monotone and non-monotone schemes to try to make it more clear, but are there any arguments with the definition so far?
The scheme is monotone and decreasing, right?
It is, yes, monotone, non-increasing.
Right, that was good.
Okay, so here's some examples. Let's just start simple. Let's say I want to get the derivative of u at some point I. Well, one way I could do it is to use, say, a backward difference. Okay, so the third argument. The third argument says, the second argument says u at this point. That's ui. So that we're not worrying about. This argument says, how does this thing depend on u at all the other points? So there's only one other point that comes up in here. It depends on u in this way. It has a negative sign in front of it, right? So this is the decreasing function of this neighboring point, right? This is not increasing in ui minus 1, so this is really monotone. So this is certainly monotone. Okay, on the other hand, if I decided to do a center difference, now I have more than one neighbor that shows up. I have to check how this operator depends on all of them, right? So again, this ui minus 1 is coming up. It has a negative sign in front of it. That's fine. But I also have this ui plus 1 coming up. This is a positive sign in front of it, right? It's an increasing function of this. And that's not allowed. So this would be not monotone. And of course, approximations like this are perfectly fine for lots of different problems, but it may not be what you want to use when you're trying to approximate this particular equation. You can combine these in nonlinear ways. Of course, what we want is some nonlinear approximations. So another thing you could do is take the absolute value of u prime. All right, if I just take the absolute value of one of these guys, that's going to not be monotone, right? Because it's really going to depend on if, u prime is positive or negative, whether we get the right behavior here. So here's a trick that you can use. You can say, well, u prime is the same as the maximum of u prime and minus u prime. True. And now I can use different approximations for this. So I say, hey, I knew a monotone approximation for u prime. That was this guy here, so let's use it. Now I need a monotone approximation for minus u prime. Well, I don't want to just stick a minus in front of this because now instead of being non-increasing, it's going to be non-decreasing. That would be wrong. Instead, I should use a forward difference discretization. So a way of writing minus u prime would be to take my forward difference and negate it, flip it around. And now what happens? Anytime I increase the value of this neighbor, the operator goes down or stays the same. Anytime I increase the value of this neighbor, ui plus 1, the operator goes down or stays the same. So anytime I increase the value of any of the neighbors, each of these terms either goes down or stays the same, and that means the maximum itself either goes down or stays the same. So this is monotone. Actually, I have some nice little simulations on this particular example that show that depending on which discretization you decide to use, you compute actually completely different solutions. Only one of them is the correct weak solution, but you can compute all kinds of nonsense just by using different discretizations. So it actually does really matter. The monotonicity is the one that gives you the correct thing. I'll show you one other example because this actually is a little bit important for terms like this, functions of the gradient. We'll do it in 1D, but you can easily generalize this just as dimension by dimension. So the thing here is that we don't really know what g is, right? And here I could use the structure of the absolute value function to do something clever. Here I don't really know the structure. So your first step is to just say, I give up, and I'm just going to do the easiest thing, which is this, which is obviously not monotone. So I put this in here, and then I say, but I can't just stop here, because this is going to break things. So I use a trick. I say I have non-monotonicity potentially in here, almost certainly in here. I need to add another term that's going to somehow outcount that. And the way I can do that is to try to include a small multiple of the Laplacian second derivative, small viscous term. And so this, I think this question came up several weeks ago, the idea of where the viscosity solution came from. It came from kind of this concept of adding vanishing viscosity to a first order operator. That's exactly what we're doing here. We're going to add a vanishing viscosity term. So ui plus 1, ui minus 1 minus 2 ui over h squared. So here, if I increase the value of the neighbors, this could go up, could go down. If I increase the value of the neighbors here, this is going to cause things to certainly go down. And the key is I need to choose epsilon big enough so that this will cause things to go down more than this might cause things to go up. Yes?
What's G?
What's G? G is just some function.
Just some function.
Yeah. So if we want the going down effect of this to overpower the potential going up effect of this, we need to make epsilon big enough, and we can decide exactly how big it needs to be by using the Lipschitz constant of this guy. The Lipschitz constant of this guy tells us how much things are allowed to go down, and it's kind of like the Lipschitz constant is the next best thing to the derivative of this thing. It tells us how strongly things are going to go down, and then or up, and then we make this big enough to outcount it. So this is monotone if epsilon is bigger than LH over 2. L is the Lipschitz constant of G. Okay, and so in our equation, our monge-ampere equation, we had this G of grad U term, right? G was our target density. The map was grad U, so G evaluated at the map is G of grad U. And you can do exactly this to build a monotone approximation of it. You can go dimension by dimension. So put in a forward difference for ux, a forward difference for a center difference for ux, for ui, for uz, for however many. And then subtract off something involving your discrete Laplacian.
So the fact that G needs to be Lipschitz makes sense. Do we impose that in general when we solve our thing, or does it come up naturally?
So for this scheme, yes, G needs to be Lipschitz.
Right.
You can weaken it a little bit. You have to be careful.
Okay.
So you can sort of take Lipschitz approximations to G if it's not Lipschitz. So say my G was like this. I might replace G with, say, G sub H, and say on the discrete level, I'm going to let it mostly be G, and then at some point I say your derivative is only allowed to hit 1 over H, say, and then I just cap it to go down like a straight line or something. Then you have to be a lot more delicate about the epsilons and how these scale. You can build things for non-Lipschitz G. Bookkeeping has to be done carefully.
So I may be jumping ahead, but what is G is the analog of what in our problem here, FH or?
So G would be the analog of FH, yeah. So here, well, G would be the analog of F, I guess. So G of grad U would be F of, would be our F here. And then this whole thing here would be our FH. The scheme is FH. The PDE operator is F. And in this particular example, it's a degenerate F in the sense that the second derivatives don't show up. Any other questions on this example? So I'm gonna come back to how do we build schemes like this for monge-ampere. I want to first convince you that actually this is the right approach. So I'm gonna outline. We're gonna basically do the full convergence proof for under some assumptions on the PDE. But the PDEs, elliptic PDEs, once you start adding in second derivatives, things get very problem dependent. So I'm going to give you the big picture convergence proof, and often things have to be tweaked a little bit from problem to problem. But this is a nice result from the 90s by Barles-Souganidis. Came up with a really nice convergence framework for if you're trying to approximate viscosity solutions. So we have monotonicity. We need some more traditional things like consistency and stability. Consistency just says, I'm actually approximating the right PDE. Right? I'm not going to say, I want to solve the monge-ampere equation, let me just solve this equal to f. That would be inconsistent. It would be monotone, but it would be inconsistent, right? So consistency says we're solving the right PDE, and then stability says that things aren't going to try to blow up on us, basically. So I have these traditional things. The scheme is consistent. I'll say consistent with the PDE. If. Okay, so consistency, we only check on smooth solutions. Right? We know the things we're really trying to compute may not have second derivatives, but in terms of consistency, we only have to check that this makes sense when things are smooth enough. So if for all C2 smooth objects, we have this. So we're going to take our scheme. I'll leave a little space here to put things. So I have my scheme. I'm going to have a point y. I'm going to put in the value of u, but it might be perturbed a little bit. Again, I put in the value of u, but it might be perturbed a little bit. And now we take limits. So we take limits as h goes to 0, right? So our grid spacing gets smaller and smaller. We take y going to x. X is the point where we're really trying to approximate the PDE. Right? And for a given point x, a particular grid may not have a grid point at x, right? So all we can do is take a sequence of y's that get close to that as we refine our grid. And this little perturbation goes to 0. And this should give us back our PDE operator. So consistency, usually just comes from doing a Taylor series, and you check that as these things go to 0, your Taylor series gives you back the actual operator that you want. Right, so in something like this, I would take ui minus 1, I would Taylor expand it about xi. Right? I have my h that pops up in there, and I have values of derivatives that come up in the air, and those exist. And then I take the limit to 0, take h to 0, and this gives me back u prime. Okay, so this is consistency, and then we want stability. Stability just says the scheme has bounded solutions. So the scheme is stable if, I'm going to say there exists a constant that doesn't depend on h, that's the important part. Such that if u is a solution of the scheme, maybe I should write it like this. Hx equals 0, then automatically UH is bounded. Okay, so this is just saying what we don't want is that, we pick an H, we pick a finite difference grid, we solve, we get UH and it's something, and then we refine it and we get UH and it's something else. And what we don't want is that these solutions are getting bigger and bigger as H goes to 0, and blowing up in the limit as H goes to 0. So this is just saying that as we refine the grid, these solutions somehow stay under control. They might be nonsense, we don't know, but they're not blowing up. Okay, so here's the nice results from 1991, something like that, I don't remember. Okay, by Barles-Souganidis. So let's suppose that F is an elliptic PDE, and it has a comparison principle. Do you remember what a comparison principle is?
Is it the maximum principle or something?
It's related to the maximum principle. So it's if I have a sub-solution and I have a super solution, the sub-solution is always below the super solution. Okay, so that's important. If PD doesn't have it, this theorem doesn't work, and you get to do something else. Okay, and let's let FH be consistent, monotone, and stable. Okay, now we take any positive H and we let UH be any solution of the scheme. Then the theorem says that as we take H to 0, so as we refine our grid, we're going to get convergence to the viscosity solution of the original PDE. Okay, of this guy. Okay, so why does this work? Alright, so we start by saying, okay, we can solve this thing for different values of H. We need some solution. We have no idea if these solutions are behaving themselves, if they're converging to anything, let alone the thing that we want. But, what do we know? We know they're bounded at least. So if they're bounded, we have well-defined limit superiors and limit inferiors of these things. So what we can do to start is define what I'll call upper and lower semi-continuous envelopes. Of our discrete solutions. Right, so as we refine each solution may not be converted to anything, it may be bouncing around, but we can kind of see what is the biggest value it's trying to hit in the limit, what the smallest value is trying to hit in the limit. So U bar is going to be limit superior. H goes to 0 of UH. And U underline is going to be the limit inferior. Okay, these things exist, right? They're bounded because we have this stability property that says all of these UHs are uniformly bounded. So U bar is well defined and it's never going to be above M. So these exist, that's fine. And what else do we know? Clearly, this guy lies below this guy, right? Limit inferior is going to be below my limit superior. So clearly, this is true. Now, what I'd like to do is show that they're actually equal to each other. If the lower envelope and the upper envelope of these solutions are the same, we're going to actually have a limit as h goes to 0. So I would like to show that these things are equal to each other and ideally equal to the actual viscosity solution. So to show they're equal, what we want to show the reverse inequality, that the upper envelope also lies below the lower envelope. So what's a tool I have for trying to show an inequality like this, comparing two solutions or two objects? What's that?
We plug them into the operator.
We're going to probably plug them into the operator. What tool do I have to try to come up with an inequality like that? I have a comparison principle, right? So what do I really want? I want to show that this guy is a subsolution. I want to show that this guy is a supersolution. And if I can do that, then I get this inequality. So we need to show that this guy is a subsolution and the other guy is a supersolution. If we can do that, then we're done. If we can do that, then these things are equal, and not only that, they're equal to a subsolution and they're equal to a supersolution, right? Which is the definition of viscosity solution. So it really just comes down to this. If I can show that U bar is a subsolution, U underline is a supersolution, I've got my convergence result. Is that okay? Do we believe that? Okay, I'm just going to show one of these. I'm going to show this is a subsolution. Then doing this one is exactly the same. Just all the inequalities go in reverse. So let's test U bar. Okay, we have a definition of subsolution. So I know how the definition starts. The definition starts by saying let's choose any smooth V such that x naught is, let's say, a strict global maximum. U minus V. Now, what is our goal? Our goal is to show that f of phi, x naught, I guess. I don't think I had this term. I just had a gradient term. we need to show that this is less than or equal to 0. If we could do that, then we know that we've passed the subsolution test. We know we can suppose that these guys are equal at this one point. Right, so again, make sure this is my u, this is my phi, here's x naught, I'm in this set. Okay, but I have to do this, working back from the definition of u bar. The definition of u bar was as this limit superior of the UH's. So I really need to work with the UH's here. Okay, so what does this being the limit superior mean? It means I can find a sequence of h's, right? Such that at any point the sequence of UH's is going to approach the value of u bar at x. So we can certainly pick a sequence, hn, which should go to 0. Okay, x naught was the maximizer of u bar minus phi. It may not be the maximizer of UH minus phi. So the maximizer is something else. So we're going to let y on be the maximizer of UH minus phi. And again, because this was defined as this limit superior, we can pick these sequences in such a way that the maximizers of these will converge to the maximizer of the original. Okay, so we can have yn converging to x naught, and we can have the value of the maximum converging to the value of the maximum, which was also phi of x naught. Again, this is just coming out of basically the definition of this limit superior, is that I can find these sequences that actually converge to the limit superior. I couldn't, the limit superior has to be dropped. Okay, now what is UH? UH is a solution of my scheme, right? So if I plug UH into the scheme FH, I get 0. Okay, so let's plug it into the scheme. Okay, so this is what I know. I also know where I'm trying to get. I'm trying to show something about how this operator acts on phi, right? So I'd kind of be happier if I was plugging phi into the scheme. If I was plugging phi into the scheme, then I could say, based on consistency, I take limits, and I recover my PD operator. So I need to make phi's pop out here somewhere. So the first way we're going to try to make them pop out is just to force them out. I say, what I really want here is a phi of yn. Of course, that doesn't happen naturally, so I better subtract it back off again and include the thing that is really here. Okay, minus phi of yn. And in my third argument, same deal. What I really want is a phi here, which is not what I actually have. So I better subtract it back off. All right, now let's see. We need to make some estimates here. What properties of my scheme that I have at my disposal that I can use to try to rearrange things here? Monotonicity, yeah. So we used stability already to say these guys exist. We think if we can get this in terms of phi, we think we're going to use consistency to bring us back to this operator. I need to use monotonicity. So what does monotonicity say? Monotonicity says something about how this scheme behaves in this last argument. Right? So we need to worry about how this behaves in the last argument. So let's just go off to the side here a little bit and say, what is this doing? Is this positive? Is this negative? What do we know about this? Can we put some sort of bound on what this can do?
So that's all equal to when you evaluate that.
At yn, yeah. Exactly. So this, we said, UH minus phi, we said was maximum at yn. So I know this is true. Now you look like you don't believe the thing you just said. You okay with this? Okay. So this is less than if we evaluated at yn. Okay, so if we're going to increase the value of this third argument, that means we're going to decrease the value of the operator. This is monotonicity. Okay, so I have phi of yn plus all of this. And I have phi plus exactly the same addition. Now, this is an improvement, right? This is an improvement because here we're looking at UH minus phi at all possible different values on our grid, and UH minus phi might not be close together, right? At x naught, they're equal to each other. If yn is close to x naught, they're close to each other, right? But farther out, they may be very far apart. But now we've pinned this down into what's going on at some yn, and yn we know is close to x naught. So we now have phi plus something small. Phi plus something small. That's good. This is getting us in the direction we want. So let's take limits. If this is true for all h, then it's certainly true as we take limits. I'm writing exactly the same thing. So what's happening here? N is going to infinity, dressing a ladder sequence. That means this superscript here, hn, is going to 0. Here we have phi, okay, yn is going to x naught. Phi is smooth, so that means phi of yn is going to phi of x naught. This term is going to 0, right? We had minus phi going to uh x naught minus phi x naught, or u bar x naught minus phi x naught. This is the same term. So here we're adding something that's going to 0. Same thing, it's going to 0. So an equivalent way of writing this would be, this is the limit, we said h is going to 0. This guy y here is going to x. And we have something small here. It's going to 0, I'll call it c. Okay, so this is fh of y. Phi of y plus our small object. Phi everywhere else plus our small object. And now we're in business. We've plugged in a smooth operator, a smooth function here. This is exactly the definition of consistency, right? That is, we take this h to 0, and we let this approach x naught, and we let this little perturbation go to 0, we recapture our PDE operator. Right, so if I trace this back, what have I shown? I found that f, when I plug phi in, if I walk up here, is less than or equal to 0. That's what I wanted. That was my goal. We said if we can show that, we're done. So this was precisely a statement that u bar is a subsolution. Okay, you make the same argument in reverse. The maxes become mins, the inequalities turn around, and by the same argument you underline is a super solution. And that means that by your comparison principle, these guys are ordered. Okay, we already knew they were ordered the other way. So now we can say, well, these must be equal to each other. The lower envelope, upper envelope are both the same. In particular, they must be equal to then the limit as h goes to 0 of UH. That limit exists now because it's sandwiched in between two things that are the same. And well, this limit is equal to this, which is a subsolution. It's equal to this, which is a super solution. So, in fact, this is a viscosity solution. Any questions on this result? It looks like you're thinking of asking a question, but you're not sure.
Yeah, I'm thinking that does the PDE we have has a comparison?
Oh, that's a great question. Does the PDE we have the comparison principle? It depends on the boundary conditions. So the short answer is in fact no. So this is a great convergence result, and it's done a lot to motivate the development of numerical methods for elliptic equations. In many cases, it can't quite be applied directly. You have to tweak it a little bit. And things that they don't do, well, they don't tell you how to build monotone schemes, so we'll talk about that. They don't tell you how to prove your PD has a comparison principle in it, may not. So for the second boundary value problem, which is the optimal transport type boundary conditions, you don't have a comparison principle, and you have to modify this a little bit. And it turns out you don't have to modify the proof too much. It gets a little bit technical, but it turns out, maybe I'll try to make this argument for you a little bit here. It turns out it's good enough to show that you've captured a subsolution. And subsolutions are automatically solutions for the second boundary value problem if you set it up right. So, what you need the actual proof is technical, and it involves being careful because none of the derivatives actually exist like you want them to, but you can do it. But here's the hand-waving version. So we look for a subsolution of the second boundary value problem for monge-ampere. So what does that tell us? That tells us something like, again, I'm just going to argue formula here and assume I have whatever derivatives I need. You can do this all rigorously without all the derivatives. So this is what it means to be a subsolution if things are nice enough. So in other words, we can think of this in terms of maps a little bit. This is saying that, if I just rearrange this a little bit, this is somehow a measure of how much mass we started with. I mean, this is the density we started with. This is a measure of how much mass we finish with after we go through the map gradient to view. So what does this say? If this is greater than or equal to, we're somehow producing or overproducing mass. Right? Here's our domain, here's our target, and I go through a gradient U map. This is telling me that I'm somehow overproducing mass, that the amount of mass in here is bigger than or equal to the mass in here that I started with. Right, if I have a subsolution. Now, if we actually have a solution, this is equality and we get equality in the masses. But if we only have a subsolution, it means we're overproducing mass, or at best we're producing the right amount. We're never underproducing. Okay, now we say, well, what about the boundary condition? The boundary condition we wrote in the form h of grad u equals 0. Right, so remember h was this sign distance function. What was important was that h of y was less than 0 if we're in the target, equal to 0 if we're on the target boundary, and bigger than 0 if we're outside. Now we're requiring not only the PDE to be a subsolution of the PDE, we're going to require that we're also looking at a subsolution of the boundary condition. The boundary condition you can also build in this viscosity framework. So if we're a subsolution of the boundary condition, what does that mean? It means that this is less than or equal to 0. So what does that mean? Start on the boundary. Here's our target. Anytime we start on the boundary, if h is less than or equal to 0, that means we land inside the target. Right? We're forced to land inside the target. And we're somehow underproducing mass here. Right, so if h was strictly less than 0, we'd be forced to land strictly inside the target. Conservation of mass says we should be able to fill up this entire target set, but a subsolution wants to underproduce mass. But at the same time, a subsolution wants to overproduce mass. So there's balance that has to happen here. And it turns out you can prove that if you have a subsolution of both the PDE and the boundary condition, this constraint says let's produce as much mass as possible. This constraint says let's produce as little mass as possible. And the only way to get a subsolution of both is if you have precise balance, that you actually have to get equality here, so you produce just the right amount of mass. You get equality here, so you produce just the right amount of mass. So it ends up, you can show that a subsolution of second boundary value problem for monge-ampere implies that actually you have a solution. You never actually have to test for a super solution, and you never have to make this comparison principle argument, basically. So you go through the whole convergence proof we just did, and almost the entire work of the proof we did was saying, let's take U bar and show it's a subsolution. For the second boundary value problem, that's actually what you have to do. You take this U bar and you show it's a subsolution, and then you make a little stability argument that says actually the limit exists, which just comes down to the stability of optimal transport, basically. So yeah, it's a great question. Barles-Souganidis doesn't give this to you for free, but you can modify them a bit to get this result. Any other questions on the proof? So the other thing that they don't tell you how to do, they don't tell you how to prove a convergence for a comparison principle, which you may not have. They don't tell you to build monotone schemes. You have to try to do that yourself. So I have only a few minutes, but let me start telling you about why that's hard, at least, and try to solve that problem. The examples I did with monotone schemes before were all for first order equations, things involving E prime. But we actually want second order operators. So a monotone scheme. For example, if I had something like this, 2xx, say in 2D, I could do standard center differences. And now let's put a minus sign in front of it, because our elliptic operator should have a minus signs. And now this is monotone, right? So if I look at any of these neighboring values, they come with a minus sign in front of them, right? I increase the neighbor, the value goes down. Same thing here, I increase this neighbor, the value goes down. So our standard center differences here are monotone, so that's great. Now, when we are looking at our monge-ampere operator, this is the determinant of the Hessian. Hessian contains all the different second derivatives, including mixed derivatives. So we could also try to do obvious things for the mixed derivatives. The most obvious approximation of the mixed derivative I know is this one, although there's certainly others. Okay, this is not monotone, right? Some of these neighbors will cause the value to increase, some of them will cause it to decrease. So it turns out the problem here was not that I was simply not clever enough with my approximation, right? So we looked at first order operators where, okay, there's ways of writing down non-monotone schemes, but if you're clever, you can do it in the right way. That's not the case here. Mixed derivative is actually not an elliptic operator. So actually, there's no particular reason why we should be able to write down a discretization that somehow inherits these properties of ellipticity. And monotonicity was somehow trying to inherit this property of ellipticity. This is not monotone, and actually you can't really do it in general. So what else? We might pick a direction. So pick some direction and say we want to do second directional derivative. The easiest way to write this out is to say, okay, we denote this with our Hessian matrix. Right, which is mu x squared, mu xx, mu y squared, mu yy, equals to mu x, mu y, mu xy. Okay. Second directional derivative, this is an elliptic operator. But if you just sort of put in the simple discretizations for these terms, you're not going to get a monotone approximation. So this doesn't lead to a monotone approximation, even though this is an elliptic operator. Well, in some cases, it might be easier to do. So this was easy to do monotone because x lines up with the grid, right? So we use the two-centered differences. So say mu was equal to, say, 2, 1. So something that lines up with the grid. Well, then you'd be again in a case where you could do a center difference discretization. Okay, this time we go I plus 2, j plus 1, I minus 2, j minus 1. Scale appropriately. And you'd be back in the business of having a monotone approximation. But this only works for a good alignment direction. Alright, so this is staying on my grid. Alright, I'm here. I use that point, I use that point. And I do center differences, but just along an angle. However, if, say, mu is equal to 1 root 2, something with an irrational part in it, or I guess root 3. Now you can't do this. This is never going to line up with your grid. True? So, in fact, there's a theorem that says you can't do this. You give me any finite difference grid you like. You tell me that you're willing to, so here I had to look a little far away. I had to go 2 grid points out. You might tell me you're willing to look 27 grid points out or 8 million grid points out or whatever. I can build you an operator, a linear elliptic operator, for which there is no possible way of building a scheme that is both consistent and monotone on that grid. So this sounds like we're in trouble. This is a result by a couple people, I guess. So Muskin and Bazal. And the idea is given any finite difference stencil. There exists linear elliptic operators, such as the second derivative in this direction, this is the rational part, for which no consistent and monotone scheme is possible. So I'm basically going to leave you there today because I'm out of time, but I will say all is not lost. There is hope in actually building consistent and monotone schemes for the monge-ampere equation. We have to be a little bit more creative in what we mean by consistency. So I'll leave you with that teaser, and then on Wednesday, we're going to actually write down consistent and monotone schemes for the monge-ampere equation and for these boundary conditions. These can both be done. You can prove that they actually converge to the weak solution. But for there, I guess we're done for today.